Okay, so as I've shown you here, we are going. So we have the moon being in an orbit, which we are assuming is a circular orbit, and then we have the very center moving with constant velocity, and we have this coordinate system in red, which we call the rotational frame or rotational coordinate system. Basically, what we are going to have here is circular motion, right? We are going to have circular. I mean, before we include the spacecraft or the third body in the system, we need to explore or review. We need to review the circular motion that you did in year 2 eventually. But so I want to do here a quick review of one important thing, which is going to be used not only for orbital mechanics we are doing, but also for the next part, which is attitude dynamics of spacecrafts. We are going to need to use that a lot. So I think it will be a very good value if we do a review of rotating frames, also known as the transport theorem. Okay? So this is quite important in rigid body dynamics for the kinematics and for the kinetics. Is we keep using these things, these rotating frames, or this transport theorem. Basically, the reason is because we have two coordinate systems. So we have one coordinate system, this one in blue, X, Y, Z. Okay? And then we have a coordinate system, or a rotating coordinate system. I'm going to call it RST. Okay? So we have this coordinate system in blue that is not rotating, and we have another coordinate system, this one in red, which is rotating. Okay? And then we have what? We have, okay, this coordinate system in red is rotating with an angular velocity, this vector. I'm putting two arrows to mean this is an angular velocity. Let's call it WR. Okay? So this coordinate system in red, this rotating frame, is rotating about this angular velocity vector. Okay? And then imagine you have a position vector. I'm going to represent that position vector like this. R. Generic position vector. So you can have a point here at the top. Okay, you can have a point here, and then, for example, imagine you want to study the velocity of this point with time. So what you have to do, you need to derive this position vector r in order to time you get the velocity. If you want to get the acceleration, you derive r in order 2 times in order to time, and you get the acceleration, right? Okay, so we have here 2 coordinate systems, the one in blue, the one in red. So this position vector r, I can describe it in either of these, in any of these 2 coordinate systems, right? I can describe it in the coordinate system in blue or in the coordinate system in red. So one more thing we need to know is these coordinate systems, they have the unit vectors that define the direction. So for the x, y, z, you have I, j, k, right? For the coordinate system in red, RST, you have L, M, N. Okay, so these are unit vectors. These are unit vectors. They define the directions of these vectors, of the axis of each coordinate system. Okay? Now, if I want to represent my vector r in the coordinate system in blue, I will say something like this. It's going to be Rx is the magnitude of the x component. X component is given by unit vector I. Ry is the component in the j direction. And Rz is the component in the k direction. If I want to represent, so this is if I represent this vector in the x, y, z coordinate system. But I can represent this vector in RST. And then that will be the component R along the L direction plus the component S along the M direction plus the component T, which is along the N direction. Okay? So this, either this or this is exactly the same vector, isn't it? This is this same vector R you have here in black. The vector didn't change. I didn't change the direction of vector R in space. I didn't change the magnitude. It's exactly the same vector. The only thing that changes is the components of the vector depending on which coordinate system you are using to describe it. If you are using the coordinate system x, y, z, the components are Rx, Ry, Rz. If you are using the coordinate system in red, the components are Rr, Rs, Rt. Yeah, these components are different. But the vector is the same, exactly the same. It's just a different way to represent it in a different coordinate system, isn't it? Okay? Does it make sense or not? All right, so if it makes sense, we are going to choose the coordinate system in red to represent my vector. Okay, and then if I derive this vector R in order to time, this is going to give me the velocity which is going to be RR dot times L plus RRS times m plus rt dot times n. Okay? In fact, let me use the color scheme, sorry. I think it's easier to follow if I use a color scheme. So let me write this in red. So the derivative in order to time of my position vector is going to be equal to r dot l plus rs dot m plus rt dot n. Yeah. Now, you might think something like this. Okay, the derivative, what about the unit vectors? I mean, this derivative should have now this term as well. Dot plus rs m dot plus rt n dot. Right? Because look, if I'm deriving this in order to time, I have here a product, right? For example, this first one, r times l. So I need to derive r in order to time. That's this component I have here, r dot times l. And then I have r times l dot, which is this component here, right? And so on for this and for this, right? It's like deriving a product. However, this term is equal to 0, this term is equal to 0, this term is equal to 0. And why is that? That is difficult to understand, so I'm trying to go very slowly. Maybe I can copy this frame to a new slide so I don't can make it bigger. Right, so let's look at L dot, okay? And I'm going to introduce here two observers, okay? One observer that is attached to this frame in blue. I will call this the XYZ observer. I mean, if this coordinate system in blue moves, this observer moves with it. Okay? And I'm going to do the same thing for the coordinate system in red. I'm going to use here another observer, which I will say is RST, for the coordinate system in red. So the coordinate system in red is rotating, right? So it means when it rotates, this observer also rotates with it. Yeah, they are attached. These observers, these two guys here, they are attached to these two coordinate systems. So, when we are making the derivative in order to time of this vector, and if we are using the coordinate system in red, so basically this is the same thing as this observer that you have here in red, looking at the vector and seeing if it is changing or not. Right? If this is any change in the vector, it means that the derivative is non-zero, exists. If there is no change in the vector, then the derivative is equal to 0. Now, looking at this first component, what is changing is the magnitude of the component in the r direction, right? So basically what is changing is if this component here, which is RR, if this is changing, getting bigger or getting smaller, do you think if this gets bigger or smaller, this observer will see that change happening or not? It will see, right? So imagine I am the observer, this is the axis, my pencil. So I'm rotating, but I'm looking at this. if I see this pencil increasing its length, I can see it, right? Even if I am rotating with it, I can see it changing, right? But now, looking at this term now, L dot, this term here, let's think on this term. What I'm trying to see now is if there is any change on this direction. So imagine again, I have the pencil you are seeing here is in front of me, isn't it? The pencil is rotating. I am rotating as well. So I still see the pencil in front of me every time, right? I am the observer, okay? Look, I rotate and the pencil rotates by the same amount. The pencil is always in front of me, isn't it? Imagine you are the observer in the blue coordinate system. Yeah, you see the pencil changing direction. But for me, I am the rotating observer. For me, the pencil is always in front of me. So for me, it doesn't change the direction. That's why this L dot is equal to 0. Because this represents the change in the L direction that is perceived by the observer in the red coordinate system. And for that observer, that L is always in front of him. Doesn't change. Yeah? Same thing for M dot, same thing for N dot. Make sense? This is a bit difficult to get in, but once it gets in, everything is so easy then. Okay. That was one thing. Anyway, I have all of this written and I uploaded already in Brightspace. So, now let's continue. Okay. What I'm going to do now is, maybe I can, oh, this is not too big. Maybe I can get this figure. Okay. What we are going to do now is I'm going to, so in fact I could have done something like this. Instead of putting here RST, I'm going to put the observer in red. So you know, is the derivative that is perceived by the observer in the rotational coordinate system. Now, what I'm going to do is, I'm going now to calculate, the derivative, and I'm going to use the blue color. I'm going to calculate the derivative of my position vector that is now perceived by the observer that is in the coordinate system x, y, z, in the fixed coordinate system. So this derivative will give me the total velocity, while this derivative we derived before this one is the relative velocity, relative to the rotational coordinate system. So this derivative is going to be equal to derivative in order to time dt of what? Of my vector r times L plus rs times m plus rt times n. Okay? So if I do this derivative with time, I get my total velocity. That can be spacecraft there, for example, right? So let's expand this derivative here. So I will have r dot times L plus rs dot times m plus rt dot times n plus rr times l dot, which is not 0 now, plus rs times m dot plus rt times n dot. Okay? So this L dot, M dot, N dot is not 0 now, exactly for that reason I just showed you. Okay? Because if my R vector is, if my axis L is rotating, you are not the observers. You see that change in direction of L, isn't it? Yeah, imagine this is the L vector, my pencil. If I rotate it, you are seeing it changing direction, right? So that L dot now is not equal to 0. So what does it represent, this L dot? Well, this L dot is going to be basically the speed at which my L axis changes direction. Well, how can I calculate that speed? Well, I can calculate that speed because I know that this coordinate system in red is rotating with this angular velocity, WR, circular motion, right? So I can say this L dot is going to be my angular velocity cross product with my position vector, which is my vector L. Right? Imagine something like this. Imagine you have a point here at the tip of this vector L. I ask you, okay, calculate the velocity of this point. What you do is, okay, the velocity of this point is going to be equal to the angular velocity in the circular motion cross product with the position vector, and that position vector is L. Right? Very quickly, imagine you have, okay, circular motion. This is the angular velocity, WR. This is L. Okay, equal to the radius. So we know the velocity is going to be perpendicular to the radius. This is the velocity. So this vector WR, how do I define it? Well, it has only a component in z direction, which is WR. This vector L okay, let me say it will have a component x, y, z component is 0. You agree? Now, my vector V is going to be the cross product of WR, which is 0, 0, WR, cross product with x, y, 0. So the result of this cross product is, in the x direction we get minus y, WR. In the y direction we have x, WR. In the z direction we have 0. Now, how do I know V is perpendicular to L and tangent to the trajectory? Well, I can do the dot product. V dot product with L should be equal to 0 if they are perpendicular, right? By definition of dot product. Let's see if that works. So we have minus y WR, x WR, 0, product with L, which is x, y, 0. This is going to be minus x, y, WR plus x, y, wr, this is equal to 0. So v and L are perpendicular. Velocity of L, or L dot, is going to be equal to v, right? So this is the same as L dot. And it is, so what you have here is WR cross product with L. Right? That's exactly what I am doing here. Okay, so I can also say that m dot is going to be WR cross product with m, and m dot WR cross product with n. For the same reason, right? They are also in circular motion. And I can now replace all of this. Before we replace, this term here is equal to this. So I'm going to replace with, I'm going to say is equal to my relative velocity. Right? So these components here, under this bracket in red, they are the relative velocity, or if you want, is the velocity that is perceived by the observer in the rotating frame. And what I can do now is take this equation and write it like this. So this is going to be equal to this plus WR, angular velocity, cross product with RRL plus RS times M plus RT times N. And where did this came from? Came from here. From here, and from here, okay? Or I can say, because what I have here is my vector R. Isn't it? Look at the very beginning. When I defined R, it's here. That's exactly what I have here, isn't it? Inside this bracket. So I can say, finally, we are getting there. We are getting there. WR cross product with R. Okay? And this, the transport term here is this one. I said this is the transport theorem, right? So this is the transport. This is the velocity in circular motion, isn't it? Angular velocity cross-product with a position vector. This is relative velocity. Okay, so this total velocity equal this is relative velocity this term transport. Okay? This is very similar with I can give you an example. A very nice example, I think. Imagine you are in a train. Let's make some aerodynamic train. You have some people seated here, but you are moving inside the train with some relative velocity, right? Relative to the velocity of the train. Okay, if you are seated in the train, your relative velocity is 0. If you are moving to go to the toilet, for example, you're going with some velocity, right? You are walking inside the train with some velocity. But what is your total velocity? Well, your total velocity so the train goes with this velocity, transport. The train is moving, let's say, at speed 250 kilometers an hour. So your total velocity is going to be equal to your, transport velocity, or let's do same order there. So equal to your velocity inside the train, your relative velocity, plus the velocity of the train, which is the transport velocity. Isn't it? So what you have here is exactly the same thing. That's why this term is called the transport. I think this analogy is good to understand, to give some logic on this. So of course, don't forget, the transport here is not a train, okay? The transport here is a frame that is rotating. Is the transport because of that rotation, right? All of that was derived in that basis. Okay, any questions so far? So you have this more detailed in the notes I uploaded in Brightspace, but the key points is this. These two observers, this is quite critical, okay, to understand, in my opinion, anyway, is my interpretation. These two observers here, you need to understand what is the difference between these two observers. And the best way is to think like this. The fixed observer, the one in blue coordinate system, is you there, sitting there, not moving, okay? And then you have something moving. Can be anything. Can be a crankshaft, can be anything, rotating, right? Can be a blade of a propeller, for example. So you will have then, imagine if it is a blade of a propeller. To each blade, you will glue this observer in red to the blade. So it will rotate with the blade. The only thing you can see if there's something happening on the blade, like the blade increasing the radius or decreasing, you cannot see the blade changing direction because it's rotating with the blade. Okay? If you understand this difference between these two observers, things make much more sense and is much easier to understand. Okay? So I spent time in this because it's going to be very valuable for us in the future. For example, well, you have one example in the textbook I upload of a crankshaft with a rod. So you have these rotation frames there. Okay? So what I would like to do today more is, because we are going to need it, is to go now to the acceleration field. And what I'm going to do is I'm going to copy this equation here, because basically this equation is like, well, you can see it in a different way. You can see this equation we derived can be seen as a new differentiation rule in rigid body dynamics. Okay? So rule differentiation, why? Because when you are deriving in order to time, you will always have to derive in this way, like you have in the right-hand side. So if this r is a position vector, what you get is a velocity. If this r is a velocity, if you derive this way, what you will get is the acceleration. Okay? That's exactly what I'm going to do. So, look, I'm going to derive, if I derive this guy in order to time, this guy on the left-hand side in order to time, what I have to do is I have to derive in order to time everything I have on the right-hand side. And everything I have is this thing here. I can copy and paste. Okay? Right, so if I continue, if I do this derivation first, if I do this derivation, what I'm going to have is, this is going to give me the relative acceleration, okay? So what I'm going to do is, I'm going to use, okay, let me put this in a, this is our magic formula to derive. So what I'm going to get from this equation is going to be, why is this blue? I'm going to get double dot okay, and then I need to derive this term with time, so I will have derivative in order to time of my don't forget that this is always the derivative in order to time that is perceived by the observer attached to the rotating frame times r plus the angular velocity times the derivative in order to time of my position vector and the one that is perceived by my observer in the rotating frame. Okay? So this one here is 0. Because of the following reason. Imagine now, my pencil now is the angular velocity vector, and I am rotating about this axis, right? Yeah? So for me, this axis is always in the same position, does not change. So the only term that remains is this one here. Okay? So we can call this So this is this first bit here. So let me use a color scheme. So this bit here is this, right? Now I need to derive the remaining of this equation. Let me copy to a new slide. Now I'm going to use, so I'm going now to so what I'm going to do now is I'm going to do the derivative, yeah? So what I'm going to do now, d dt of WR cross product with R. This is equal to WR dot times R plus WR cross product with R dot. Okay? Yeah, but R dot, let me keep this one. But R dot is equal to, we have seen that R dot, come on. R dot is equal to this, isn't it? Right? I'm going to copy this. So this is my r dot, okay? Right, so okay, so putting everything together now, my final acceleration, if you want, r double dot perceived by an observer in the x, y, z is going to be equal to this, which is going to be equal to this first component here, which I'm going to copy all of it to here, plus all this component we have here, derived here at the end, or we can even do better. Now, just some simplification here. Right, so we keep this one. So this term here is equal, so this is the same as this. Okay? So these two terms are equal, this and this. So I'm going now to write the final equation for the acceleration. I'm going to leave here, this component is the relative acceleration, or is the acceleration perceived by the observer attached to a rotational frame. Then we have I can say a transport component, which has two components. One is this one, which is the tangential acceleration. Why is this green? Okay, let me write this. Tangential acceleration. The other term we have is due to this cross product here, which is, I'm going to add here, this is the WR, cross product with WR, cross product with the position vector R. This is known as the normal acceleration, and I'm going to explain what this is. So you can say these two added together, they are the transport. Yeah, think of the train again, the transport component. And you have a last term, which is the infamous what? When you have 2 times the angular velocity cross product with a relative velocity. What is the name of this last term? When you have a body rotating, and then imagine you have, a rod in a crankshaft mechanism, and then you have a slot in the rod, and you have a point sliding in that slot. So the rod is rotating, and at the same time that point is sliding inside that rod that is rotating. When you have these two things, you have these two components that gives one acceleration, which is the Coriolis acceleration. Okay? Coriolis acceleration. Oh, I don't have space. So this term I'm going to do this way because I don't have space, is the Coriolis acceleration component, okay? And this is your final formula. For the acceleration. Basically, think on these three big components. Relative acceleration, the one perceived by, for example, going back again to the rod with a slot and the pin sliding. If this pin is sliding with constant velocity, relative acceleration is going to be zero. But if this pin is accelerating inside the slot, then you will have a relative acceleration, okay? Well, that will be perceived by this observer. And then you have this second big component, which is the transport component, which includes two parts. Tangential acceleration, normal acceleration. Why do I call these names? Well, because one, in circular motion, so if you have a point here, the tangential acceleration is going to be this component, WR dot, cross product with position vector, tangential to the trajectory. And the normal is going to be this one, WR, cross product with WR, cross product with R. This is in the radial direction, pointing to the center of the circle, okay? So we call this the normal, and we call this the tangential. In order for you to have tangential, you need to have an angular acceleration. WR dot is an angular acceleration. So if you don't have angular acceleration, you don't have tangential component. Well, for the normal, you don't need to have any angular acceleration. Even if you are with a constant angular velocity, you still have this normal component of acceleration. Well, this one you experience, for example, if you go in your car, this is centripetal acceleration as well. You experience this when you are curving in your car, right? Even if you are curving with constant velocity, don't forget this term is a velocity. This one is a velocity, v. So if you are turning with even if you are turning with a constant velocity and turning with a constant angular velocity as well, you still experience a centripetal force, isn't it? That centripetal force is because of this. And Newton's second law, of course. So you have WR times WR times R. This is an acceleration, right? This is your AN, normal acceleration. If you multiply this by the mass of your car, this is going to be equal to your centripetal force. Right? And now look at this. I think these things are interesting. So I'm diverging a bit, but the reason is, imagine this is your car here. You are curving. You are at this point. Okay, I said here the acceleration is pointing inwards, the circle. But the force you experience is outwards, isn't it? Think on if you are in a car, in a curve, you experience a force in the opposite direction. Why is that? It's because of Newton's second law. Because this term, MA, you move to the left-hand side, then you have minus M mass of the car times WR times WR times R. This signal minus here means that your centripetal force is going to be in this direction and equal to this, right? Right, so I don't want to give you more pain today. I think it's enough. So this was, look, this is something you should have done in year 2 or year 3, I don't know. I'm just giving you my interpretation of this thing because we are going to use this a lot, right? So what I propose you guys to do is try to, there's an example, the crankshaft rod example I uploaded in. If you want to get more into this, because everything was, I delivered this maybe too quick, eventually, I don't know. But if you want to get more familiar with this, if you want to practice a bit, I put an example I saw from beginning to end, velocity field, acceleration field, using the transport, all these concepts, and the derivation I did here is there as well. So check that on Brightspace and get more familiar with this, okay? Because this then, once we go to spacecraft attitude dynamics, and also the three-body problem we didn't finish yet. The three-body problem, I did that introduction and then I did this revision because we are going to need this to finalize the three-body problem. So I don't want just to give you these equations in three-body problem and then, what is this? Yeah, you will think, where did this equation come from? Yeah, so yeah, I think for today it's already a lot. Thank you guys very much. You behaved so well. You can interact more with me, you know that. If I'm going too fast, just stop me. Yeah, because I'm embedded on this thing and I keep going. I just keep going, all right? So stop me. If you don't understand something, just stop me and really it's really a favor you're doing me, putting questions, because otherwise I'm here talking. Time is not good. Yeah? All right, so have a nice weekend. Enjoy. We continue next week with the three-body problem, okay?